Okay, it's 1 o'clock. I think I'll have to stay here so that it's audible to everybody. So good afternoon. So I just want to remind you that there is a lab today for 16 students. So the first half of Monday section, okay? So I have individually sent you emails and also shared the list in the last class. So I hope you know now who is supposed to attend today, okay? So let's just do a quick recap of what we looked at in the last class, okay? So in previous classes, we began with Ohm's law, and then we went on to complex circuits with superposition principle, and also we looked at Thevenin and Norton equivalent circuits, okay? So if the circuit gets really complex, then one way to simplify and represent it in a simple circuit is by using Thevenin and Norton equivalent circuits, okay? Any questions with that? Right? So that was all about DC components with simple to slightly complex circuits, okay? So this is our roadmap, okay? Let me first pick the pen here. So we are here. We did the basic circuits, V and I, that is voltage and current relationship in simple circuits using Ohm's law, and then Thevenin and Norton circuits, okay? Today we are going to do the AC circuits, okay? So, and in the lab, you will be using microcontrollers to test the basic circuits, okay? So don't worry about the programming of microcontroller and the details about the microcontroller, the architecture, different pins. We'll come to that in last section of the class, okay? Last 2-3 classes, I will talk about different types of microcontrollers and different ways to program them, and how do you use different type of microcontrollers in different applications, okay? So, but now today we'll talk about AC circuits, okay? So, well, you use DC circuit, right? Why do we need AC signal? Or why do we need AC power? Signal means power. Why do we need AC power? Why not we use just DC? Take a guess. It is. But do you know how? Well, think about the famous fight between two famous scientists, Thomas Edison and Nikola Tesla. Finally, Nikola Tesla won with his AC motor, right? Why do you think AC motor was successful, or AC power was successful? Yes, somebody mentioned because the energy losses are minimal. But does anybody know why energy losses are minimal? So of course we don't use DC for everything, right? For example, batteries give you DC power. So, well, so we know P equals VI, right? So that's voltage and current. So that's the power. So for a specific power, if you want to transmit the energy across large distances, the power loss in the lines is P equals I think I'll I square R. So for a constant power, if you want to transmit, you have to have certain voltage or current, but the power loss in the transmission line is I square R. That means you have to minimize current. That means you have to make the voltage higher. So what you are getting here, 120 volts, should be ramped up, stepped up to much higher voltage, then the current becomes less here. If the current becomes less, then the power loss in the transmission lines will become low. So that means you can reduce the power loss if you can step up the voltage. So that's why AC is preferable, because you can step up and step down the power. I'll tell you how to do that. So when you step up the voltage, you can reduce the transmission loss. And that is not possible with the DC power, okay? Does anybody know why is it not possible with the DC power? Why can't we step up? So same thing applies. As long as you can step up the voltage, you're reducing the current. If you reduce the current, you're reducing the power loss. Does anybody know how the voltage is stepped up or down? Okay, so let me so does anybody know what is this? It's a transformer, right? So a transformer is a device that steps up or steps down any power or voltage, okay? So how does it do? So basically a transformer is nothing but a loop of ferromagnetic material, okay? And if you wind current, or sorry, if you wind wires across two arms of the closed loop, then if you supply voltage in one loop and take the power on the other side, then your voltage to voltage relationship is given by voltage in by voltage out, or primary by secondary. They call it by many names. It is ratio of number of turns that you wind to get the current in and current out. So, or you can also say it V primary by V secondary equals N primary by N secondary. Okay, so this is a simple relationship. So that means if you take a ferromagnetic core and wind wires with different ratios, you can either step up or step down voltage. Okay, so it's as simple as it is. Okay, so that means you have a way to step up or step down. That means you can minimize the power loss. But why can't we do DC current with this? Any thoughts? Well, for that, you need to know a little bit of magnetism. Let's not go there. Basically, you need to have time varying voltage here in order to change the flux density in the secondary. Then only you can transfer the power between two windings. Okay, if it's a DC power, then it's constant. There is no variation in the flux. Hence, you won't get any induced voltage in these coils. So this is the basic principle. That's why AC can be stepped up and stepped down. By doing that, you can minimize the transmission loss. Okay, so that's the first one. Second one, you can minimize the transmission loss. And also, we'll come to this one. We'll look at the exact mechanism, how a motor works, right? That's in our actuator class, slightly later. So a motor and generator work on the same principle. So basically, you have a rotor that's made out of some magnetic material, and then a stator that has some windings that has current. So if the current is AC, then you can get the torque. If you don't have AC power, then it will be really difficult to change the poles manually or by some other mechanism. The motors become complex if you don't have AC power. Okay, because with AC power, you go to one polarity and then another polarity. By doing that, you are switching the poles, and you are switching between the repulsive and attractive forces, which makes the motor move. If you don't have AC power, you can still have DC motors, but you will have to have contact brushes. You'll have to have a slightly different mechanism, which are prone to wear and other problems. Okay, and likewise, it's easy to generate power with AC. It's easy to generate AC power with generators. That's because when you have rotational motion, then the voltage signal that you get out is also in a sinusoidal form naturally. Okay? These are the reasons why we use AC signal, why Nikola Tesla or Nikola Tesla's technology or work became more popular and eventually was adopted, okay, over Thomas Edison's. Right. So how does the AC signal look like then? Or how does the AC power look like? So it's governed by this equation. So V of t, okay, I'll use this just here. So the voltage varies with the time by this equation, okay, in a AC signal. So this is the amplitude of the voltage, and it varies in a sinusoidal function. Omega is the angular velocity, t is the time, and phi is the phase difference, okay? So a period is the distance between, or the time between two peaks, okay? And 1 over period is the frequency, or frequency is also equal to omega by 2 pi. Omega is the angular velocity or angular speed. So basically it's radians per second. So if you want to get frequency, frequency is nothing but per second, right? That means you have to divide by radians. So omega by 2 pi will give you the frequency in hertz, okay? So that's what is here, okay? So this is the peak to peak. That's peak to peak is twice the amplitude, and here is the phase angle. So these are the things you need to characterize any AC signal. But we don't go so deep. We need only amplitude. That is quite important for us. However, when we are dealing with AC components like capacitors and inductors, we'll have to use slightly different equations than what we have used in Ohm's law, okay? And an AC signal can be not just a sinusoidal signal, it can have a slightly different function, but it will be oscillating around a mean, or it may not. For example, this signal can also be considered as AC but it's not alternating at 0. It could be at some other value, okay? So in order to deal with some of the AC components, we have to know complex numbers, how to deal with complex numbers, okay? So I'm sure you might have come across complex numbers, but let me give a quick review of complex number. So a complex number is represented by this format. So this is your real part, and this is your imaginary part, where i's value is equal to square root of -1, which is an irrational number, right? So you try to somehow get rid of I, or you convert I to a rational number, or simplify it. So if you have I square equals -1, okay? And the magnitude of the complex number is square root of the real component square plus the real part of the imaginary component square. That's your magnitude. And the phase of a complex number is tan inverse of B by A, that is the imaginary part by real part, okay? It is represented by phi. So we'll be dealing with complex numbers whenever we deal with capacitors and inductors, okay? And capacitors and inductors are integral part of many mechatronic systems, and we use them quite often. You know, right? Capacitors are everywhere. So they're basic storage devices as well as for filtering signals and even for amplification. We'll see how we can use them in different applications, okay? So here is a quick bonus question. If I is root of -1, I square is -1, what is 1 of I? Okay, the people who are watching online, so please type your message. I may not be able to see now, but I'll see when I go back, okay? And somebody asked, how do I grade the 5% of classroom interaction? Okay, this is how I grade. When I ask these questions, people who are watching online should reply in the message box, and people who are here can raise their hand. And of course, I'll be asking in every class, and everybody gets a chance to message as well as say it in the class, okay? No? 1 over I. Yeah.
Negative I?
Say that again.
Is it negative I?
Yes. That is negative I. How did you do it?
That was a guess.
Actually, it's right. So all if you multiply 1 over I into minus I by minus I, or sorry, not minus I, just I by I, okay? That becomes I by I square, right? So then I square is -1. So I by -1, minus I. Okay, so we will use similar trick when we are dealing with AC components. When we are dealing with capacitor and inductor, if we have a denominator that we want to get rid of, just like here, we'll multiply, okay? So here is another example. I'll do it quickly. This is these two are two complex numbers. If x plus y, you just add the real part and add the imaginary part, okay? This becomes 5 plus I, okay? X minus y equals 1. So sorry, this is 1 plus 3I, okay? And x into y. This side of the screen is not working properly, so I'll have to always work in this right hand of the screen. So x into y equals, so this is again multiply, just like you do the normal multiplication. So this is 6 minus 3i plus 4i minus 2i squared. Okay, that is 6 plus I minus, this becomes, that becomes 8 plus I. Okay, so it's just a quick refresh for you because we'll be using this later on. So if you have x by y, then so if you want to do x by y, then you have 3 plus 2i divided by 2 minus I, right? Then you use the multiplication trick because we want to get rid of the denominator, right? So what will you multiply? I think you have to multiply 2 plus I, 2 plus I, okay? This becomes, denominator becomes 2 square minus I square. Okay, we use a minus b into a plus b is a square minus b square trick here. Okay, and then you multiply this as usual on top, the numerator that you will have 6 plus 3i plus 4i plus 2i square. Okay, so this becomes, this is 10, sorry, this is 7 minus 2. So 4 plus 7i divided by 4 plus 1, that is 5. So you have 4 plus 7i divided by 5. Okay, so that's your division. Clear? So okay, then let's that's a quick recap of how to deal with complex numbers. Okay, because we'll be dealing with them, with the complex numbers, when we want to work with capacitors and inductors. Okay, so we'll still, if we have an AC circuit, we'll still use Ohm's law, but instead of resistance of the entire circuit, we'll have to use impedance. Okay, now in AC circuit, it's not just the resistance that accounts, because in AC circuit you have other components, that is capacitors and inductors. Remember, so V of t equals L into di by dt in an inductor, and in a capacitor, I of t equals C into, this is, sorry, this is E, this is I, okay? And C into dV by dt. Okay, so here the resistance is not a rational number. So the resistance offered by the capacitor is not a simple resistance. It's something called impedance, which is combination of resistance that is due to the property of the material, and reactance, which is because of change of signal. Okay, so impedance has two inherent properties, resistance as well as reactance. Okay, so the impedance of a resistor, even in AC circuits, is equal to R, whereas the impedance of a capacitor in a AC circuit is equal to 1 by j omega c. J is same as I here. In circuits, people have been using it as J, so we are keeping the same nomenclature. Okay, we'll not change it because it might lead to confusion. So J is nothing but I, which is my root of -1, square root of -1. Okay, and the impedance of inductor is ZL, that is J omega L. L is the impedance, inductance, that is measured in Henry. C is the capacitance, that's measured in Farad. Okay, so these are the three components in any AC circuit. Okay, combination of these three simple components can lead to circuits that can be used for many applications, that can be used for filtering a signal, that can be used for amplification, that can be used for voltage division, and so on and so forth. Okay, so just with these three components, we can do a lot of things. So then let's look at a simple circuit that has a capacitor and a resistor. We'll start simple first. We'll just look at capacitor and resistor. Okay, so you have a AC signal that's represented by sine wave inside. That's AC signal. So this is the common ground. This is just like saying you have a full circuit here. Okay, so this is represented this way, so it means the same. Okay, so now in this circuit, the capacitance of the capacitor is 1 microfarad, and the resistance of the resistor here is 1 kilo ohm, and the voltage in is 1 volt, and we are asked to calculate the voltage out at resistor, or voltage drop across the resistor, for two frequencies, one at 100 radians per second and another at 10,000 radians per second. Okay, so sometimes they might ask you at 40 hertz or at 400 hertz. Okay, so you have to convert it into radians per second. Radians per second is the default unit of, or SI unit of, the omega. Okay, that we saw in our formulas. So in this case, it's already in radians. So the frequency is from radians to frequency, you divide by 2 pi. So this is, if you divide 100 by 6 point something, 6.2, it's about 18 hertz. Okay, 18 hertz or 180 hertz. So at these two frequencies. Okay, so these are given. So this is a simple loop, right? One loop. So we can use Kirchhoff's voltage law here. So voltage drop across this one plus this one minus this one, or this minus this should be equal to 0. Or you can use voltage divider rule, right? So V out equals V in into, you are taking voltage drop across this, that means R, divided by the entire, not resistance, but the impedance, because we are dealing with the AC circuits here. Okay, so this is Z total. Okay, so Z total, what do we have? That is total impedance. That's equals V in into R divided by Do you remember what is ZC, the impedance of the capacitor? 1 over j omega c, right? So that means you have R plus 1 over j omega c. Okay, that's your voltage divider equation. Okay, so I've written the same thing here. Okay, so if you substitute, this is what you get. So now 1 over j omega c, right? Let's simplify that. 1 over j, if we simplify it, 1 over j or 1 over I becomes minus j or minus I, right? So that means this is, you can substitute that 1 over j as minus j, so you have this left. So that means now you have a real part and an imaginary part. So now if you take the magnitude of voltage out by voltage in, then you have, this is the magnitude of that is same as R, right? So the magnitude of this complex number is square root of the square of the real number plus the square of the imaginary component, right? So that's what we have here. And if you solve for that, so this is what you get, okay? So the magnitude of V out by V in is this, where omega is your radians per second angular velocity or the frequency, and R and C is resistance and capacitance, okay, divided by the same parameters in different formats. So if you substitute them with the values here, 1 microfarad and 1 kilo ohm, so, and we are, first case, we are taking omega equals 100 radians per second. So if you substitute at 100 radians per second for omega for C equals 1 microfarad and R equals 1 kilo ohm, WRC is 0.1, okay? So WRC square is 0.01. So if you substitute these numbers in here, this is what you get. So that means what you have here is the magnitude of voltage in, the magnitude of the ratio of voltage in by voltage out is equal to voltage out by voltage in is equal to 0.1 at 100 radians per second, okay? Let's do the same thing for 10,000 radians per second, okay? So what do you think it will be? Well, let's see. So the same thing, if you substitute, instead of 100 radians per second, if you substitute 10,000 radians per second, you get WRC equals 10, WRC square equals 100. So if you substitute that, so it's 10 by square root of 10, 10 square plus 1, that's 10 by square root of 101, which is almost equal to 1, okay? So you at 100 radians per second, your ratio of voltage out to voltage in is 0.1, but whereas at 10,000 radians per second, your voltage out to voltage in ratio is 1. What that means is at higher frequency, whatever voltage out you get is same as whatever voltage in you give, okay? So that means, so this resistance or this capacitance has least effect. So whatever voltage you are inputting, you're getting the same output, okay? Whereas at lower signals, at lower frequency, it's 10 times lower, okay, at 100 radians per second. So what that means is you can use this simple capacitor and resistor circuit, and you can design it such that at low frequencies, the voltage out is almost equal to 0. Okay, in our case, when we use 100 radians per second, we got 0.1. But if you do it for 10 radians per second, it will be closer to 0. Okay, whereas at higher frequency, whatever you put in here, you get out here. So that means this is nothing but a filter. Okay, if you have a signal that has high frequency, it doesn't have any problem coming out of this circuit. Whereas if you have a signal that has low frequency, it doesn't come out. So that means it blocks low frequency. Okay, so this is a nice high pass filter. Okay, it allows high frequency signal to come out. So where do you think you can use it? High pass filter. So you want only the high frequency out. Or where you want to block low frequency. There are many applications you can use it in. For example, if you are just looking for high vibrations at larger frequencies in any structural element, then you can use high pass filter that will only give you output that has that has signal so that is associated with high vibration. Okay, so but you need to convert that mechanical vibrations into electrical signal. Okay, that will again look at strain gauges in our sensors classes. There we will, but you need to remember this at that time. Okay, so that we can make use of this high pass filter along with our strain gauges to only recognize high frequency oscillations. Okay, so this is it is a very simple circuit, right? Just a resistor and a capacitor is enabling you to filter low frequency signal. So we can use the same thing to do the opposite. You can also filter high frequency and allow only the low frequency signal. So if you want to do that, instead of taking V out here, you take V out here. This is your V out. You got the idea. So then you will be blocking high frequency signal and allowing the low frequency signal. So if your output is there, you do the same thing again. It's a voltage divider, right? Now instead of your V out equals V in into your ZC now, right? Because that's where you are taking the V out, and this is ZT, right? Now you will have a complex number here on numerator as well as denominator. You just again simplify it, and you will get a simple expression that when you substitute the frequency, resistance, and capacitance, you will see that it blocks high frequency signal and allows low frequency signal. So you can make it a low pass filter. Okay, so those are very useful when you are dealing with sensors, because sensors, they will be catching all sort of signal from the environment, and you know which signal is yours. You know that your signal will be a low frequency signal, then you have to use low pass filters. If your signal is high frequency signal, then you have to use a high pass filter. Okay, so if you plot V out by V in versus frequency for this circuit where you are taking V out at the resistor, so at low frequency at 100 radians per second, you will have just 0.1, and at 10,000 radians per second, you will have 1. Okay, and you will have in between values. Okay, that means at high frequency here, your ratio of V out to V in is equal to 1. Okay, so this is what you need to show. If I give you a circuit and say, show me whether it's a high pass filter or a low pass filter, you need to calculate for different frequencies and show it in a graph like this. Okay. So we have 10 more minutes, and I will solve one more example. Okay. So we'll make the circuit slightly complex now. Okay. Now we have an inductor, a resistor, and a capacitor. Okay. So here is the resistor, here is the capacitor, and that is the inductor. And resistor is 1 kilo ohm, capacitor is 1 microfarad, and inductance is 10 millihenry. Okay, and you have been asked to calculate voltage out or voltage drop across the resistor at a frequency of 5,000 radians per second. Okay, and your voltage in is 110 volts. Okay, so 5,000, if you divide by 2 pi, that is 6 point something. This is about 900 hertz. This is a very different signal. It's a very high frequency signal at 110 volts. That means it has a lot of energy. Okay, so okay, how will you do it? Voltage out across the resistor. Yeah.
Should we calculate for a total impedance first?
Yeah. So, but why do you need to calculate total impedance of the circuit?
Finding voltage out.
Yeah, that's true. So how will you calculate voltage out? So this is a simple one circuit, right, with one loop, right? It's one loop. So what do you do in one loop? So you have to apply KVL, Kirchhoff's voltage law, right? This is your loop. So that means you have 3 components and a AC and a power source, right? So you can either do voltage divider. So this is voltage divider with here and the remaining to here, or you can do the KVL. Okay, so if you apply your voltage divider rule, V out equals, you want V out across R, right? So R into V in divided by now the total, not the resistance, but the impedance, because we are dealing with the AC signal, right? So Z total. So Z total will have R, capacitance, and inductance. Okay. So what is your Z total then? Z total is impedance of resistor, impedance of capacitor, and impedance of the inductor. Okay. So let's substitute the individual impedances here, right? Impedance of capacitor, we know 1 over j omega c, and impedance of inductor is omega L, j omega L, right? And the impedance of resistor is just R. Okay, so if you substitute that, this is what you get. Okay, and again, see here you have 1 over j. So if you take it up, this becomes negative. So that means this becomes R plus j omega L minus j by omega c. Okay, so this again, now you can simplify, take j out. So now you have a real part and an imaginary part. Okay, so you have a complex number. So now you can take the magnitude of the total impedance, so which is magnitude equals square of the real part plus the square of the imaginary part and the whole square root. Okay, so you take the whole square root of the sum of the squares, and this is your equation. And if you substitute omega, you are asked to calculate at 5,000 radians per second. Okay, and your inductance is 10 millihenry. So if you substitute that there, and here your omega and c, you have microfarad, so it's 10 to the power minus 6. So this is what you get, and if you solve that, this is your total impedance. Okay, now if you substitute your total impedance in your voltage divider rule, then this is what you have. Okay, so the voltage out at resistor is 108.8 volts. Okay, so that's should be lower than the voltage in, which is 110 volts. Okay, is this clear? So just by knowing how to handle complex numbers, you can solve circuits with AC components in them. That is circuits with capacitors and inductors. Okay, and these circuits are useful for filtering signals. Okay, they are also useful for amplifications. Okay, so now in this circuit, your voltage out is 108, which is slightly smaller than 110. So if you want to make it, so if you want to make V in equals V out, what do you need to do? So where is your, let me, so what do you need to do if you need to make V in should be equal to V out? It's in the equations. Just look at the equation. Yeah.
You lower your impedance.
Yeah, but how? So that's true. You lower your impedance, but which one? Inductor, capacitor, and how do you lower?
It's the lower resistor.
Well, no. Just by varying the frequency. That's what I mean. Not by changing the physical components. Components are the same. Yeah. Yeah, I'm talking about we are varying the frequency.
So we want to use the lower frequency.
Is that right? So here, this is your equation, see. Okay. So here is your frequency terms. So that means you want to minimize this, right? Your total impedance. How do you minimize that? That means make this 0. Right? That means your omega L should be equal to 1 over omega C. Right? So that means omega L minus 1 over omega C equals 0. That means this is, so C is, so you will have omega square, that becomes omega square LC minus 1 equals 0. So omega square LC equals 1. So omega square equals 1 over LC. So omega equals square root of 1 over LC. That should be the condition for you to make V in or to minimize the impedance. Okay. So when you do that, when your omega square is equal to 1 over LC, that means that's when the circuit is said to be in resonance. Okay, so your angular velocity or the frequency should be square root of 1 over impedance, product of impedance and capacitance. Okay, so yeah, I think that's the end of the class. It's 1:15 now. So in the lab today, this is the first in-person lab. So we'll be testing the simple circuits with the voltage divider and using microcontrollers. Okay. So first 16 people of Monday section, please come to the lab. Okay. Any questions so far? Okay. Thank you.